Let us now talk in some more detail about the quadratic conic sections. Let us start with a parabola. So a parabola can be defined as a set of points, and this is a property independent from what we discussed above in terms of conic sections. And so it can be thought of as the set of points equidistant, which is a fancy word for at the equal distance, from a fixed point, which we'll call f, and so it is called focus, and a fixed line L, called the directrix of the parabola. And so the picture here is roughly as follows. We have a fixed line so this will be the x-axis, and what we will do is we will place the focus f at some point on the y-axis here. So let f has the coordinates 0, p, so it lives on the y-axis, and let the directrix be parallel to the x-axis, like so. And so we'll make sure that the parabola passes through the origin. And so the way to do it is to make sure that the origin is exactly in the middle between the focus and the directrix. So since the origin is at the equal distance between f and L, so these two distances are the same, the origin belongs to this set of points. And so basically, by this geometric property, what it says is every point on the curve, say this one, is such that this distance this distance from point F to this point on the curve is the same as the distance from point P to the line L. And so these two distances I want to denote as equal. Let's see, this one and this one. And this holds for every point on the curve. So for example, for this point here, again, this distance is equal to this distance, and so on. Okay. So let us obtain the equation, Cartesian equation, for the set of points. Let's call them P with coordinates x, y, that satisfy this geometric property. So let the vertex, the focus of the parabola have coordinates 0, p, and the directrix, as we just discussed, is symmetric with respect to this point. With respect to the origin is to this point. So these two distances are the same. The line L is parallel to the x-axis, and so it has the equation y equals minus p. Right? So then this ensures that the distance between the origin and the directrix L is the same as between the origin and the focus F. So the moral is the following. If we compute the distance from F to P, it is the same as the distance from P to L. So the distance from F to P, or maybe let's write it backwards. Let's put it this way. For any point P with coordinates x, y that lies on the parabola, the following distances are equal. So the distance from P to F must be equal to the distance from P to L. Okay, and so now is the matter of computing these two distances. So we need the distance of this segment here and of this one here. So this angle here is a right angle. So the distance from P to F can be computed using the distance formula, which says to compute the distance between 2 points, you take the square root of the differences of respective coordinates. So you have x minus 0 squared plus y minus p squared equals the distance from P to L. So distance from P with y coordinate y to the line y equals minus p is y plus p. So here I am effectively saying it's y minus p. And I put an absolute value because I don't know a priori if p is above the line y equals minus p or below it. So this formula applies to both cases. Now, what I need to do at this point, I want to simplify this equation. So I won't do it here. I'll just sketch the idea of what you have to do to simplify this. So to simplify, you want to square both sides of this equation. And so after some manipulations, after simplifying this, canceling out similar terms and so on, which I won't go into right now, you end up with the following equation. You end up with x squared equals 4p times y. And so you remember that p was the distance from the vertex of the parabola. So here the vertex coincides with the origin because you have the symmetry of the curve with respect to the origin, and so O must be the vertex. And so P is the distance from the vertex to the focus, or currently from the vertex to the directrix. And so this is the equation of a parabola that has focus at the point 0p and directrix given by the equation y equals minus p. And so there are various alternative forms to this equation. For example, the one that you can obtain by interchanging x with y, like so. Oops. And so interchanging x and y gives you the following. And this is the standard trick you can apply to all the other curves as well, and we will do so in the future. But right here, interchanging x and y gives you that the equation y squared equals 4p times x is the equation of the parabola and so this is the equation of the parabola with focus P0 and directrix x equals minus p. So you see what I did was I interchanged the roles of x and y, and so that means I interchanged x and y in the equation, and then I interchanged the coordinates of the point here, and then I interchange the y for x in the equation of the directrix as well. Great. And so this gives me two ways of thinking of a parabola. So this would be the vertically oriented parabola, of course, and this is the horizontally oriented parabola. And so if you recall the equation of parabola as we know in the standard form, this of course is not going to be surprising to you, because you can think of this as y equals x squared divided by 4p. So it has the standard form of the equation for a parabola. Nothing surprising here. And similarly here, this is clearly a parabola oriented horizontally. But you can ask all sorts of questions about this form of the parabola. So for example, you can ask things like find the focus, directrix for the given parabola. So you can go back and forth between the geometric properties of a parabola and its analytic equation. So for example, this question here asks to find the geometric properties, focus and directrix, given the analytic equation. And so the equation we have here is y squared equals y squared plus 10x equals 0, which we're going to rewrite as y squared equals minus 10x. And so by comparing this equation with the second equation for parabola, we see that this is a parabola oriented horizontally. So it's a horizontal parabola with focus. And so it's the focus with coordinates p0, according to what we had here, and p must be minus 2.5. So since this here is for p, p is minus 2.5, and so we get the coordinates for the focus minus 2.5, 0. And directrix given by the equation x equals 2.5. And so that's what you get if you take x equals minus 2.5. And so we have obtained the geometric properties of this parabola, and then we can easily sketch its graph. So it's a parabola oriented horizontally. It opens clearly to the right. Whoops, sorry, let's see. No, it doesn't open. It opens to the left because we have the minus sign over here. So that can also be seen by thinking of where the focus lives. So the focus is right here at the point minus 2.5, 0. And you see it's placed to the left of the origin. And then the directrix is oriented vertically. So this is our directrix. And so using this information, you can easily sketch the graph of the parabola. It passes through the origin and looks something like this. And so for all equations of this form, of course, the parabola always passes through the origin and its vertex is always at the origin. And so you can ask various other questions, but the idea is that using the information that we gave here, you can go back and forth between the geometric properties of a parabola and its analytic equation. So that is the primary idea here.